Hello, y'all. Darrell Lee Beber Jr. here, back as promised on Wednesday to do some more thermodynamics. So I've already read the section I'll do a problem on right now. And as y'all heard on Wednesday, the bane of my existence is proofs. And this happens to be another proof, but this one seems very relevant. So it doesn't seem so bad. But basically, they want us to redo a proof that was done in the book, uh, which is not so bad. It just changed the uh, layout of the proof a bit. So I'll scroll to it here, share my screen, and get started. And as always, if you haven't already subscribed, like all that good stuff, let me get to 1,000 subscribers. Let's see here. So I noticed the window doesn't seem to be as wide as it normally is. Maybe I made an adjustment somewhere. I forgot I did. All right, that's better. So y'all can see the problem there. Consider a classical degree of freedom that is linear rather than quadratic, and then E equals CQ for some constant C. An example will be the kinetic energy of a highly relativistic particle in one dimension, written in terms of its momentum. Repeat the derivation of the Equipartition theorem for this system and show that the average energy is E equals KT. So the uh, original derivation they're talking about is done in this section. So I'll see about doing these side by side. I was actually meaning to, for all my hatred of proofs, I was actually meaning to actually do this derivation again. Turns out I have to. That's vertical. So we have that in the middle. And pretty sure I'm going to need more than one page. Right? So Equipartition theorem. So I'll put quadratic linear. The linear one is the one that we need to do for this problem. So the quadratic degrees of freedom, you can see in the book on the left, is CQ squared, and the linear equals C absolute value of Q. So C is a constant, and Q is a coordinate, i.e. X, TX, LX. The partition function, and I should have that down already. inverted, hopefully. So here it is here. Technically, this should be I. This should be the same for both. So Z equals sum Q E negative B EQ equals sum Q E negative beta EQ. So what they did here was they insert the actual energy EQ equals C Q squared. So here EQ equals C Q. So this equals the sum Q E negative beta C Q squared. And this equals the sum Q E negative beta C absolute value of Q. And what they're going to do is multiply this by 1 in the form of changing Q. And then we can simplify this, or I guess I should say complicate it really, by putting 1 over changing Q on the outside. Sum Q E negative beta C Q squared, changing Q. And on this side, it equals 1 over changing Q. Be sure to drop a line. Let me know if you have any questions, any comments. If I make a mistake, I welcome you letting me know. Beta C absolute value of Q, changing Q. And you can see how they approximate this sum. We have a whole lot of parts as an integral. So that becomes 1 over changing Q integral over the entire range of values e to the negative C Q squared dq. And this becomes 1 over changing Q integral negative infinity to infinity e. Did I leave off my beta? I think I left off beta. Negative beta C absolute value Q dq. And now they get tricky. And they say x equals I'll say x squared equals beta d q squared. So here, x squared equals, and maybe this doesn't work here, but I'll still try it, equals beta c, absolute value of q. So x equals square root of bc q, and here x equals square root of bc, okay, becomes square root of bcq. I'm not actually sure if taking a square root of an absolute value, yeah, so the absolute value is going to be only positive. So here, negative q equals q, positive q equals q. So whatever it is going to be q, positive. So I'm just plugging that in there. One moment, I'll get some lotion. My hands feel dry. Be right back. So this does change things a bit, but I believe that still works, since whether you put a positive or a negative q inside the absolute value, you come up with a positive q that will keep the square root real. So I think we're safe here. So let's keep going and see. So dx equals square root of bc dq. Oh crap. And this does complicate this on the other side. So this equals square root of bc and q 1/2. So dx equals square root of bc 1/2 q. Solution. This should be 1/2 q dq using a chain rule. Yes, this is definitely. Well, let's keep going and see what it does. So if I substitute this, substitute this for x squared and this for dx. So I think it's something that I don't have to take the square root on its side, since there's no square. I think that's what the difference is. So I'll just say x equals beta c q, and dx equals b c. So that's pretty much b c q dq. I'll say that that's what's going on here. So now we have z equals 1 over square root of q, the integral E, and BCQ squared is x squared, so that's negative x squared, and dx is square root BC and dq. So dq is dx over square root BC. All right, so I have to solve for dq there. So I'll just allow that step to stay uh, implicit. So this equals 1 over changing q, 1 over square root BC integral negative infinity to infinity e negative x squared dx. And that's what they have there. So on this side, we have equals 1 over square root of q integral negative infinity to infinity. E to the x, well, negative x, and dq is dx over dc. So this equals 1 over changing q, 1 over bc, the integral negative infinity to infinity, e to the negative x dx. Right. So it looks like I'm matching what they have on the left side, and I'll assume that the right side is equivalently correct. And actually, I could show this explicitly on this side. Dx over bc equals dq. So, right. So that's the Boltzmann factor. We're saying the integral over x is now some number. So this is just a number, as well as, well, I don't know what this is. That gives the solution for a Gaussian in Appendix B. This is worthwhile to take a look at it real fast. Gaussian integrals, e to the negative x squared. All right, well, it just says what it equals. So this becomes 1 over square root of q, 1 over square root of bc, square root of pi, that's the integrand of the even function. Integrand from 0 to infinity is just half this. Let's bring all makes use of two-dimensional integral. Okay, yeah, I remember the professor actually showed this in class. Uh, and I did this before in Quantum 1. We had to do a lot of integrals like this, but it's been a while. Yeah, well, let me make a video on this one day called, Gaussian integrals. Know there's a trick when you do multiples of them, or there it is, like if there's something multiplied by something else. Right, let me make a quantum video to that effect. All right, so for the right one, like all there is to do is to do the integral. So if I take this integral, that's 1 over square root of q, 1 over bc, and going to be e to the negative x divided by negative 1, infinity, negative infinity. Then we have 1 over square root of q bc, negative e to t negative infinity minus plus e to the infinity. Zero and infinity. It does make sense. Perhaps we do have to do something else with this square thing. Forget what there is a relation where you can break absolute values up into multiple. I don't remember exactly what it is. I shall check this integral just to make sure. Yep, it says it does not converge. I was considering making this into two integrals. I don't think we can, I don't see how we can assume it'll be the same. Like if I said 2 over changing q bc integral 0 to infinity e to the negative x dx, since infinity does give us something, equals 2 over changing q bc. And now we have e negative e to the negative x negative infinity 0 to infinity. So we have 2 over changing q bc, and now we have negative e to the negative infinity minus plus e to the 0. So we have 2 over changing q bc, and this is minus 1 over infinity plus 1, and this is 0. So we have 2 over changing q bc. So z for the you call it quadratic degree of freedom is 1 over changing q square root of bc square root of pi, and that's the solution from the book. For the linear one, z equals 2 over changing Q, B, C. The book, what does it do with this change in Q? I see it just puts it in C. So that equals everything but B is in C. Call that C over square root of B. And this will be C over B. Right? So in the book, the expectation value is 1 over Z, partial derivatives of the partition function with respect to B. There's a negative that I missed. So Z over here equals C B negative 1/2 over CB equals negative 1/2 C B negative 3/2 B. On this side, Z equals C uh, B negative 1. So partial derivative of Z over partial B equals negative C B negative squared. And it seems to be matching what's in the book. So E equals 1 over V is square root of B over C, then times negative 1/2 C B, so negative 3/2, and this will equal negative B over C, C, B to the squared. So the C's cancel. And on this side, we have negative square root of B over 2. And hold up, I think I'm missing a term or something. I think I see what they're doing. At first, I missed a negative here. This will be B to the 1/2 and B to the negative 3/2. So this is, oh, there's a negative there. So this will come positive. Then we have 1/2 B to the 1/2 minus 3/2 equals 1/2 B to the negative 2/2. So that's 1/2 B to the negative 1. This is what they have. And B is 1 over AT. So this equals 1/2 1 over 1 over AT. So this equals AT over 2. And on this side, we have I did the same thing, left off a negative. This becomes positive B to the 1, B to the negative 2. So this equals B to the 1 minus 2, which equals B to the negative 1, and B still equals that. So we have just 1 over 1 divided by KT, which is this KT. And I believe that's what we were supposed to prove. I don't even remember. Welcome, who's watching. Be sure to drop a line if you have any questions. The problem said it should equal KT, and it does. All right. One thing I'm still unclear about is exactly why we can use this do vaguely remember that if you have an integral over infinity, both ends, you could just double it and take half of the range. And we know that negative infinity, since the integral is negative, becomes positive infinity, it just becomes infinity. But the positive infinity becomes zero. So I just kept the positive infinity in place and so it went to zero to positive infinity. So this exponential was a positive exponent, then we'd have to take the negative infinity to zero. So that's just a trick to keep in mind. All right, guys. So got that problem done. I'll go ahead and call it. Oh, what's going on, Catherine? Oh, go ahead. I know somebody was here. I'll keep on going for a while. Yeah, interesting problem. I hate proofs, but apparently I'm going to have to do some of them. I'm getting better at them, I guess. How's everything been going with you? I don't even remember what problem I have to do next. I'm going to scroll up and see. 6.32 only, part A. All right. Doing good as well. Battling to catch up on this homework, but I'm a little bit behind since I was focused on the exam I had coming up, which was worth it. I did presumably well. That reminds me, I need to do the redo. Matter of fact, I need to practice some of those exam problems. Maybe that's what I'll do. Have about what? I mean, I have some time. Let me pull up. The professor actually gave us some. Um, gave us the files to practice, even though we have our old exam. I did relatively horrible on the last exam compared to the previous ones, but I can get half of the points back, so I still end up with a B on it, which is good. I just found out I got an A in my relativity class, so that's good. I turned in my final assignment earlier. My final assignment was a paper. I'm very good at writing, so I wrote that up and turned that in. He pointed out some things I could improve, so I made those improvements. He gave it the go ahead. So I'll get an A out of that class. So I'm glad about that. And I could just focus on my remaining three classes, which I have a project for and two final exams. So that's what I'm preparing for at the moment. Yep, thanks. Appreciate it. Yeah, I'm glad. Went out the way. You know what? I think he emailed us the exams. No. Where do you put this at? Right. I'm going to find these exams and I'm going to do a few problems. So the exam, I love this class. I love this professor. And I'm learning a lot in this class because he's not, uh, he's very good about giving you the proper information you need. And this is related to my Cosmo class, which I dropped because that guy was intent on giving you as little information as possible. Apparently, he didn't even let people see what they did on the first exam. I actually walked out the exam and went straight to dropping the class because that class was horrible. A lot of the other people dropped, at least a few that I'm aware of directly. I know they were unhappy with that class. Right. So I think I gotta go to the. Oh, I forgot. I downloaded them all anyway. So I've made a promise to do at least a few of these problems every day so I can be ready for the final. All right. Crap, I'm at 5% battery. If I'm not finished by the time it gets to 2, I'll plug it in. All right, so let's look at one that I know I can do real fast. I'm going to just uh, make some space here. So let's say we have a thermodynamic process that has pressure on one axis and volume on the other. So this can be, for instance, if you have a piston and the piston is uh, compressing air inside a container. So this is a container, and there's air floating around the container here. So if I were to push the uh, container in, I will have to do work on the system. And I can't actually remember the tip my professor gave me. If you do work on this system, is it positive or negative? I don't remember. All right. So hopefully it'll come to me doing this problem. Okay. You do work on this system. If you compress it, the volume will change and the pressure will change. So the way the problem works is we have a thermodynamic process that looks like this, and we'll call this VO, and we'll call this 2VO, and we'll call this PO, and we'll call this 2PO. Now give me a moment while I try to look up in my notes what the professor said about uh, which direction is positive work. These details. Suffice it to say, on the last exam, I lost a point on this problem because I got the sign wrong. So when I asked him about that, I'm trying to remember this in case I get this problem or won't like it again. Catherine says, yes, it's amazing when you have a good professor or tutor, but there was an old dog in psychology with some disgusting views who didn't return for his mentorship. Oh, man, I can imagine what those views are. Yeah. I've been watching a lot of, I guess, I don't know if it's just to prepare myself in case something happens and I do have to teach like a K through 12 school, or just to inoculate myself against ever believing I should ever do that. But I've been watching a lot of why I quit teaching videos, and I guess is the uh, kind of the opposite. And with those people, is the administrators, which are the like principals and stuff, and the students going crazy. I don't know which one is worse. Well, I guess I know which one is worse. Because like I was able to just drop that class, like I think I don't know if I did it intentionally, but a lot of times I took more credits than I needed, and if I passed all the classes and all the classes were good, well, I mean that's good, even though it's difficult. Uh, but then if one of the classes is crazy, like I was able to drop that class, and I still have 12 hours. So I can still potentially get university honors this semester. It should be my third semester. I mean, I'm still in a place where it's possible, but I don't know if I'll do it. Now I gotta remember where I put that note. I think I noticed my thing is not updating anymore. Maybe I need to clear some memory or something. Right. Well, I was gonna say I don't remember what uh the detail is there. A former place. Right. Oh crap. This thing oh, I had this maximized. Okay. I'll just keep on going with this problem. And I'll see if I can tease out. I mean, generally the equation is work equals negative uh PV generally. See if I can remember where I put that thing at. Here it is. So hold up. All right. That's right. So in this case, I have to go by uh each scenario. So this way it is here is actually opposite the way I'm doing it. So here the volume is decreasing, the pressure is staying the same, and work is positive. Because volume, so I'm doing work on the system is positive. Here the volume is increasing, so the system is doing work on me, so work is negative. And here the volume is not changing, so work is zero. And we're using this equation here. All right, I think that's what I needed. I'll copy this. All right, so we do work on the system. Didn't I say that? I guess I didn't remember it. Work on system is positive. So if I could just remember that. Let's look at this. And this one is going opposite what's going on in this picture. So here is going this way, and this way. So here the volume is increasing, positive change in V. So the system is doing work on us. The work is negative. And again, we're using work equals, I guess I should say dW equals a negative P change in V. Even though I remember there was a negative there. Yeah. All right. So I guess technically, I don't even want to think about it. I was about to start fiddling around with this negative thing. But overall, if the volume decreases or increases, the system is pushing out, so work is negative. Here, the volume is staying the same, so work is zero. And here, the volume is decreasing. There was a negative change in volume, so work is positive. And he also mentioned how the magnitude of this thing is obviously longer, right? So the magnitude of this is obviously longer than that. So overall work will be positive in this system. So we can say total work on the system will be positive. And the work is also equivalent to the area here. So basically similar to the problem I did earlier, I could turn this into an integral and say work equals integral the pressure as a function of volume dV, and thus the area under this curve is work, and this is the bottom of the curve there. So I can say you can get this area easily by saying if I was to make that a square, area is length times width, which is going to be 2v naught minus v naught times 2p naught minus p naught. So that equals, and this is really 2 area, equals 2 uh, v naught minus v naught p naught. And Catherine says, yes, that makes sense. Awesome. And what's the last thing I have to do here? So that's twice work. Okay. I know. So the entire area, if I make this a, oops, if I take the area of this entire triangle, it's twice the work. Okay. So twice the work is the area of that triangle, because the triangle is actually only half the square. If I take the whole thing, that's twice the work. So twice the work is that is area of the square. So now we can say work equals 1/2 P naught V naught, and is positive because this dominates the interaction. Okay, so we have that. And the energy of the system, if you go back to the same spot, at least the change in energy is 0. As I went back to the exact same spot, similar to have a take a object and I move it up and move it down, is back to the same potential energy. And the first law of thermodynamics says that what is it? Work. I don't remember the first law. Let me look it up. Thankfully, we have a formula sheet we can use on the exam. So let me search this. I remember what the variables are, but I always mix it up. Okay, here we go. So it's up there at the top right there. So change in U equals Q plus work. So the change in the energy of this thing is going to change according to the work from the piston and the energy going in from the uh, candle. So Q, the last thing I need to get is change in U minus work equals 0 minus 1/2 P naught V naught. So that means that the energy is negative 1/2 P naught V naught for this entire process. So to solve what they wanted us to ask for the process, for the entire thermodynamic process, the work is 1/2 the one pressure unit and volume unit. The change in energy is 0 since the thermodynamic process goes back to the start. And the change in heat is going to be negative T naught V naught over 2. So that completes that problem. And I'm right at 2 on my battery. It's awesome. Always good to see you, Catherine. Thanks for dropping a line. So always good to know somebody's still watching. Help me go a bit longer. And what I likely do, I know I'll do that quantum on Saturday. So you can tune in. I'll do the quantum. We're putting a particle in a magnetic field, and we'll talk about Zeeman changes and fine structure. It's amazing. Today, my quantum professor was talking about, uh, crap, I didn't think about it. We were doing numerical solutions to the Schrodinger equation. Dude is deep. Dude is deep. But I'm just amazed at how much. I think I mentioned it before, how much goes into the stuff we have. Like I was talking about the thermodynamic stuff in the power plants, and like we were talking about where to build a power plant. We have to take into account moving the electricity, for instance. And we talk about quantum stuff, like why things bond. Like my thermodynamics professor, the professor for this class, was talking about how um, okay, there's common carbon monoxide poisoning. And that's because the receptors in our body that absorb oxygen also could absorb carbon. Uh, but it so happens that when you look at it thermodynamically, the receptors, when it connects with a carbon, reaches a lower energy state than with oxygen. And what a bond is between molecules, going back to quantum mechanics, is when you put particles together, if they reach a lower energy state, being together than apart, that's what we call a bond. And it takes the amount of energy to equal that decrease in energy with them being together to break them apart. That's the bond energy. Well, since the carbon is linked with oxygen, you have carbon monoxide. Since the carbon in that pair causes a lower energy state than oxygen by itself, which is really O2, carbon as carbon monoxide can bond with our receptors easier. So you can have a lower concentration of carbon monoxide than oxygen, but still that carbon monoxide will win. And that's why even with a smaller amount of carbon monoxide, you can get poisoned, which is how it's so convenient. Like if somebody's trying to do that, the holes with the pipe thing, or that's why they say don't run your car in the garage because you might not realize it. It might not smell so bad, but the carbon monoxide has a whole lot easier chance to attach. And I believe it's fumes that cause carbon monoxide. Whatever causes carbon monoxide uh, 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 is bad. It's like 4 times. It bonds like 4 times faster than oxygen. So it's such a big deal. But all of that, you know, we could see people getting carbon monoxide, so we know why it's happening. We know it happens very easily. But when you actually do the math and the science behind it, you can see why, and it has to do with quantum mechanics and thermodynamics and how the molecules bond with your receptors to cause a lower energy state. It's amazing. All right, thank y'all for watching. I'll be back Friday. We'll look at Saturday. We'll look at uh, quantum and putting a particle in a magnetic field. I may be back Friday on this channel or Thursday. I'll see, but I may just be offline for those 2 days. And I'm going to check my seal detector tomorrow. I know they're fine, but I regularly check them. Good idea. And that's what professor said. That's why we need this, because the carbon monoxide, it could get you. All right, Catherine, good seeing you. I'll see you Saturday, if not before. Everybody else watching, you'll have a good night as well.